Hi all. I wanted to revisit question 4 because I've been getting a lot of these comments and questions from other people about, the idea of work and when something rolls and it goes down, and I just want to clear up something about work and static friction and rolling. When I went over my answers are correct on that one as far as I can tell. No one has pointed out anything that is wrong. Especially for part B particularly. The part B down here when we're talking about comparing the block versus the cylinder. I really want to demonstrate to you why it is that when the cylinder rolls, the friction doesn't do any work on the system. And I really, this is a very subtle point about rolling motion that is not usually discussed. So it's kind of interesting that they put this in a question because in reality, this is a very subtle and kind of a complicated point. So I'm going to start with this problem is, let's not talk about energy first. Let's just talk about the forces and the torques that are happening. So I'm going to consider a cylinder, and for the sake of convenience, I'm going to assign it some letters. I'm going to say this is a cylinder with mass m. It has a rotational inertia. I'm going to say it is it has a 1/2 mr squared. Now, where r is the radius of the cylinder. This is technically for a uniform density cylinder, for those of you who know what the different I values are. But you do not need to know that in AP Physics 1, so you don't need to know where they came from. Just imagine that I did a uniform cylinder and it has this rotational inertia. Now, if I were to draw a free body diagram, what's happening in this situation is that there's gravity acting down, there's a normal force acting perpendicular, and there is there's a frictional force acting perpendicular to the ramp. Hopefully most people can understand that part, because most people understand that you need something to act as a torque to cause this thing to spin, and it is friction that does that. Now, what kind of friction is it? The kind of friction is static friction. Now, static friction is a tricky friction, because static friction does not equal mu. This is another big misconception. It does not equal mu times the normal force. Okay? Static friction is a reactive force. That means, what it really means is the maximum static friction is equal to mu s times Fn, where mu s is the coefficient of static friction. Okay, so what does that mean? That means that the static friction can be anything from 0 to mu s times Fn, or anything in between. For example, I give a demonstration where I have my calculator in my hand right here. This is what I always demonstrate to my students. Okay, right now, how much static friction is there? There's none. There's only a normal force up and a gravitational force down. Now I'm going to push a little bit with my finger. Now is there static friction? Yes, it's opposing me. So is static friction equal to 0, or is it equal to what? Is it equal to mu mg? No, because right now it's 0. Why would it equal to mu times mg? It's equal to 0. Mu is not 0 at this point. It's not like the coefficient of static friction is a property of the surface. That's non-zero. So static friction is a reactive force. It responds to an external force. It is just enough force that is necessary. Once you exceed the maximum static friction, then the surfaces begin rubbing. And then you have kinetic friction. So that's how you have to think of static friction. You cannot assume the static friction equals mu times Fn. Second, how do I know it's static friction? Well, it's static friction because the wheel is rolling without it's rolling without slipping. That means the wheel is not making any rubbing motion with the surface. If it were, then it would be kinetic friction, but it is static friction because of that rolling without slipping part. Okay? So this is what we know about the system right now. Now, I'm going to enlarge the free body diagram so that you can see a little bit better here. So this, I have mg, I have static friction here, and I have normal force this way. Now, there's two things I can talk about at this point. Oh, actually, let's decompose the mg into its two component forces. This is theta. This is mg cosine theta. This is mg sine theta. Okay, so now I've decomposed gravity into its two component forces. Oops, let me put an arrow down here. Okay, so let's analyze what's going to happen here. Now, I do not know what the static friction is. It has to be less than or equal to mu s Fn. So first, I can do net force equals ma. So that the net force down the ramp, is going to be mg sine theta minus the force of friction is equal to the mass of the block times its acceleration. Okay. So that's one equation. So how do I figure out the acceleration? You can at this point. I pretend I know what m and theta are. I don't know friction. I don't know a. But I can also look at the net torque is equal to I alpha. Okay. Now the net torque, force of friction is the only torque we have. It's force of friction times the radius of the object here, of the cylinder. And it's equal to I, which I said in this case was 1/2 mr squared times alpha. Now, alpha, if it rolls without slipping, this is a key part about rolling without slipping. There's two things that are happening. It's not rubbing against each other, but the other thing is that alpha is definitely equal to A over R. Okay, this quantity only holds for rolling motion as long as it's rolling without slipping. Because what it's telling you is about the angular speed is in line with its translational speed. So that as it rolls, it moves at just the correct velocity. This is not always true. Okay? For example, think about like if you ever see a car, it accelerates super rapidly. The wheels spin, but there's no translational motion. It's just burning against there. So alpha and A don't necessarily have this relationship for rolling, only when it's rolling without slipping. And I'm talking about the acceleration at that point there. Okay, so this part becomes 1/2 mr squared. Oops. A over R. And so that will cancel, and that will be 1/2 ma times R is the force of friction. The R's can cancel here, and you get the force of friction is 1/2 ma. You can then plug that into here, and I can find the acceleration. So mg sine theta minus 1/2 ma is equal to ma. So add it over to here, I get mg sine theta is equal to 3/2 ma. The m's cancel, and so a in this case would be 2/3 g sine theta. This is me simply calculating the acceleration simply from net force in it. I'm not talking about energy. I'm just simply doing kinematic. I'm going to do kinematics here at this point. Now, I know what the linear acceleration is at this point. So what is the linear velocity at the bottom of the ramp? So if this thing rolls down the ramp, he's going to achieve a certain velocity down at the bottom. Okay, he travels a length h0. Okay, so let's just use that. Let's just say, let's use our kinematics. You're going to have v squared is initial velocity plus 2a delta x. And in this case, I know the acceleration. The initial velocity is 0. I release it at rest. And so v squared is going to be 2 times 2/3 g sine theta times the displacement. And the displacement as it goes down the ramp is L0. Okay, so the final velocity is going to be the square root. Well, let's just solve for v squared. V squared is equal to 4/3 g sine theta times L0. Okay, so that's the velocity that it would be traveling down. And let's talk about its angular velocity. Angular velocity, if it's rolling without slipping, is equal to v over r. Okay. So we would take this quantity, the square root of all of this, or actually, let me just solve for omega squared instead, so I don't have to deal with the square root. So omega squared is v squared over r squared, and that's equal to this quantity over r. So it would be 4/3 g sine theta L0 over r squared. So we did a lot of computations here, but we found what omega squared is and what velocity squared is. And now I can tell you what the total kinetic energy here is at the bottom. The total kinetic energy is 1/2 I omega squared plus 1/2 mv squared. That's 1/2 times I, which we said was 1/2 mr squared, times omega squared, which is this quantity, plus 1/2 m times v squared, which is just this guy here. Okay. So what did I find here? This is 1/4. That cancels with that there. The r squared here is going to cancel. So I have mg, so I have 1/3 mg sine theta L0 plus this 2 cancels with that plus 2/3 mg sine theta times L. That adds up to a whole mg sine theta times L0. Okay? And L0 sine theta L0, if I look at this angle here, sine theta is equal to opposite over hypotenuse. It's h0 over L0. So you get h0 is equal to L0 sine theta. So therefore, I know that this is, the sine theta is just mg h0. Now, what have we just proven? We've just proven this is the gravitational potential energy it started with. We just proved that for this particular eye, okay, that it rolled down the ramp and had the same kinetic energy at the bottom of the ramp as it did at the top of the ramp. And I didn't use energy or calculation. I didn't make an argument about it. I simply looked at net torque equals I alpha and net force equals ma and used kinematics. Okay? That's what we've proven here. Now, let's do it with a different eye, and let's do the exact same scenario. And let's so I want to point out a few things. The total energy is the same at the bottom, but let's see what we got for the velocity, the translational speed. It's the square root of 4/3 g sine theta L0, and remember we said the L0 sine theta is just h, so it's 4/3 g h0. Okay. This is what we got for the translation. I want you to keep this in mind because now we're going to do it for another cylinder with a different eye, one that is maybe a hoop, okay? And we're going to show the same thing, that you will still have the same energy at the top and the bottom, but that the translational energy will be different. Okay? That's what we're going to demonstrate, and hopefully that will clear up what's happening in this scenario. Okay. So now I'm going to consider the exact same scenario, but now say I is equal to mr squared, and this would be more like a hoop if you want to look up rotational inertias, or they're technically called moment of inertias traditionally. If you want to look at different moment of inertias or rotational inertias for different shapes, but it's going to be the same mass, but the mass is going to be distributed more to the outer edge of the cylinder, so it's going to have this I mr squared. So let's see what's different in our equations. So what's going to happen is when we redo some of our equations, this 1/2 mr squared is going to just be mr squared. So let's start with our basics again. The net force equals ma. That is mg sine theta minus force of friction is equal to ma. And net torque is equal to I alpha. But this is force of friction times r. But now we're going to have mr squared times alpha, and we just said when you roll without slipping, alpha is equal to a over r, and so this is equal to mr squared a over r. The r's cancel, and you get mra is force of friction times r. The r's cancel, you get force of friction is equal to ma. Okay, then I'm going to plug that into there. I get mg sine theta minus ma is equal to ma, or mg sine theta, moving this to the other side, is 2ma. The masses cancel. And so here I have 1/2 g sine theta is equal to a. Okay? Now, this is a different acceleration. Remember, with a different hoop, I had 2/3 g sine theta. So it's going to accelerate. So hopefully you can see, obviously, by right now, that the translational energy at the bottom is going to be the same. But I want to show that it has the same total energy. So we're going to use, again, kinematics. V squared equals V0 squared plus 2a times the displacement. The V0 squared is 0 because we release it from rest. So V squared is 2 times 1/2 g sine theta times the displacement, which we said was L0. And that is equal to g sine theta L0 because the 2 and the 1/2s cancel. Okay, so what is his translational velocity? It's the square root of g sine theta L0, but we said sine theta L0 is actually equal to h, so we're just going to call this square root of gh. Okay, so look, this guy has a very, very different linear velocity than this guy. And I didn't change the mass. I didn't change anything about the friction. Notice I didn't even use the coefficient of kinetic static friction because you don't know what that doesn't matter. The coefficient would only help you figure out what the maximum static friction is. It is unnecessary in terms of this context. Both of these objects in this scenario have the same static coefficient friction. It's same surface. I didn't assume a different surface. Same surface, but they have different velocities simply because of the way that the way the mass is distributed. Okay, so let's look at the omega squared again is equal to v squared over r squared. That would be gh over r squared. And so now we have omega squared, we have v squared. Let's look at the total kinetic energy. At the bottom is 1/2 I omega squared plus 1/2 mv squared. This is 1/2. And remember, the I for this guy is mr squared. His omega is gh. Omega squared is gh over r squared. And then plus 1/2 times his mass times his v squared, which is gh. We found right here, right? So here the r squareds will cancel, and you get 1/2 mgh plus 1/2 mgh. Oh, sorry, it should be h0. I should be a little more careful. Use the same letters as I was using before. And I get mgh0. So again, I proved that this guy with a different rotational inertia, the energy is still conserved. The kinetic energy at the bottom matches the gravitational potential energy at the top. Okay? But different translational velocities. So it definitely matters the shape of the object. Some people were trying to explain or prove that it doesn't matter what the shape of it is, as long as the same mass, it will have the same translational velocity at the bottom. If you guys had done more labs, maybe you might have like some intuition. But there's some experiments we run. If you do a disc that's a solid wheel, I don't know if you've ever seen a time trial bike. Time trial bike is a disc wheel. If you've seen it, like when I say time trial for like a Tour de France or when you're qualifying for speed, wheels, they have a disc wheel where the mass is distributed more evenly because it's easier to rotate. See, wheels where the masses are near the ends are harder to rotate. They take more torque for you to rotate at a higher speed. Okay, so definitely you roll different things on the hill. They're gonna go at different speeds, even if the same mass, same ramp angle, same thing. They will move at different speeds, and this is why we can do conservation of energy. Because we just proved that I didn't do any calculations with work or energy. Notice that all my calculations were just from Newton's second law and the kinematic equations, right? And torque, and some assumptions about rolling without slipping. But no energy calculation did I did to show what the speeds are. All right? So one of the consequences of when you do rolling without slipping, energy is conserved. If energy is conserved, that means their work external has to be zero, because external work is the change in energy, and that has to be zero. So that means the frictional force did not do any work. If it did work, we wouldn't expect the energy to be the same at the bottom of the ramp as it was at the top of the ramp. We would expect a different amount of kinetic energy from the top, because that would mean there's some work that is causing a change in energy in my system. And that is simply not the case. Static friction does not do any work. That's the consequence of everything we just derived without doing any work or energy calculations. Well, other than to prove it. I only proved what the energy was the same afterwards, but to derive the velocities and angular speeds, I did not use work, I did not use energy, but the result is the same. Energy is conserved, the static friction does no work on the system. Now, in this particular problem, when they're asking you about whether or not, when you had to block down the ramp, and it has the same kinetic energy at the bottom, that is a coincidence. You cannot prove, hopefully I've just demonstrated, you cannot prove that these two definitely have to have the same velocity because it would depend on the rotational inertia of this block. Okay? You cannot prove that they have to have the same velocity at the bottom. Okay? So, therefore, this question is not about proving whether or not they have the same energy. They're just simply saying that they have the same energy. That's a stated fact. And you have to explain why they have the same energy. Okay? And it does because it just so happened that the work done by friction on this block happens to coincide with the amount of rotational kinetic energy this guy gained. But that is not true for every possible scenario or every possible block. That's just in this scenario, that is what has happened. I hope that helps clear it up. And I speak emphatically because I think this is really interesting and really, really a subtle point about rolling. I like the question in that it is a difficult and subtle question. And it really tests your understanding of energy, rotation altogether. And I know there's going to be a lot of people who made the mistakes and kind of mixed that part up. But I really wanted to emphasize like why it is that all of those things are true. It's really interesting that like I use dynamics and these results just pop up, right? Because these are known, you apply different rules to apply different principles. It can get confusing. They all stem from Newton's laws originally, like all of these concepts do. So I hope you find this helpful.